I've been looking at search engine optimization. We're going to leave that now for a time and look at some other things, and we'll return to search engines again later. I wanted to get moving on the whole preparing images for the web so that you can work on your assignment too, and so that we can get moving on that. So the first thing we're going to look at is just the whole process of digitization and how that might work. So this is quite detailed, but we're going to skim past a lot of the details. I'm going to try and restrain myself a little bit because I have a whole module on this stuff. So we're not going to try and fit a whole module into one or two classes. But we'll hit the important points. So when we digitize an image, we want the image. Digitization is just representing things in numbers. So when we digitize something, we want a numerical representation of it. And it's nothing more than that. We sometimes use the word digital synonymously with super mega high quality, but that doesn't mean that at all. I mean, it can be digital and be crap. So typically when we are digitizing an image, we divide it up into rectangles. Now, they're usually squares, but they don't have to be squares. We break it up into non-overlapping rectangles, and then we get the average, say, lightness and darkness of that space then in there. So the average darkness of each rectangle will be calculated and then assigned a value. So if we look at this one, this rectangle here, that's an easy one. That's probably in here or here. So so we have like a range of values, but we don't have infinite precision. So it just fits into one of these slots here. And in this case, we've got 16 slots in this example. Those are called quantization levels. So we could take any shade of gray and say, where does it fit in here? And if it fits, if it's in the slot here, then we'll call it that. A high quality black and white image would typically have 256 quantization levels. 256 is plenty. So we're just taking a tiny portion of the image, seeing how light or dark that is, and then depending on how light or dark it is, it gets assigned to one of these slots. And so we end up with what we call pixels. And so each pixel then its color is the average of the area of the image that it represents. And you're familiar with the idea of pixels, I'm sure already. Now, the more pixels you have, the better the quality. So one of the measures we have when we're scanning photographs, for example, is Dpi Dots per inch. Even in the metric world, you'll still see Dpi used as a measure, or even on screens as well. You might see a display as this many Dpi dots per inch. And obviously, if you have in a square inch, if you have an inch of a photograph, and you're scanning that at like 800 pixels by 800 pixels, that's going to be quite dense. It's going to be quite high quality. But if you scan it at less, it won't be so good. And that'll have an impact too on the size then at which you can display it. So if you take a picture with a not great phone and you make it into a poster, it's not going to look great. One of the things, say, an iPhone or an iPad does quite well when it takes pictures is it has higher resolution. And of course, the more dots you have per inch, the greater the size. Which brings us to something we mentioned when you were doing web development fundamentals. If you have an image that's, say, 4,000 pixels wide and 4,000 pixels high, and it's going to be displayed on the screen at just 400 pixels by 400 pixels, well, that's 100 times bigger than it needs to be. So about having a huge image and then displaying it really, really tiny. Because the person has to download the big image and pay for 100 times more than they would for an image that's just 400 by 400. But of course, if you have an image that's only 400 by 400 pixels and you want to make a poster of it, you're not gonna fare well. So you have to think hard about and be mindful of how the image is going to be used and where it's going to end up. Now, so I'm going to show you now the consequences of reducing the number of pixels. There's a good chance that the presentation software is going to maybe blur things, what we'll see. So at 600 by 400 here, it looks pretty good. If we go down to 300 by 200, I can just make out on my screen that I can start to make out the pixels. Can you guys? If we go down to 150 pixels by 100, you can start to see there now. It's getting pixely. Now, if you were at the number 8 bus stop there, and you could see the screen, it would look fine. You wouldn't see the pixels. And at 75 by 50, it's just quite pointless, really. No. So the more pixels you have, the better the quality is going to be. But if you consider when we went back here, we said that we get the average lightness and darkness of each rectangle, and then we assign it to one of these values. Well, the more possible values you have, the more quantization levels you have, the more accurate the representation is going to be. But also, the more you have, the number of bits you're going to need for each one. So if you have 256 shades of grey, which is quite typical, you need 8 bits per pixel. In this example here, we've only got 16 shades of grey, or 16 possible quantization levels. So in that case, you only need 4 bits per pixel. So that's another dimension in which you can reduce the quality, change the quality. So the more bits you use per pixel, the better the quality. So here we've got 8 bits per pixel. So we've got 256 shades of grey here. Now I suspect in this image we're not actually even using all 256 shades. I don't think there's any pure black in here. And I don't think there's any pure white in here, for example. So when we go down to a fewer number of pixels, 5 bits per pixel, I don't think you can even see a difference. No, I don't think there's much of a difference there. Here at 4 bits per pixel, we've got, how many would that be? 16 shades of grey. So if we could actually zoom in and see the pixels, we could maybe count up the shades of grey. And you know what? I think even at 4 bits per pixel, this is holding up quite well as an image. So maybe it was a bad example, I'm not sure. At 3 bits per pixel, I can just make out the difference there on my screen. The first place you'll notice it, and of course then when you see it, you know where to look as well. So the first place you'll notice it is where there's kind of gradient, where there's sort of a smooth transition from one color to another, from one shade to another. So if you look here at, we go down to 8 bits per pixel, you can see up here, starting to, just if I can show you there with the cursor. Up here, can you see there it's starting to go? Can you see that on your screen? Knowing now where it's starting to give first, if we actually go back to the 4 bits per pixel, you can see it's a bit ropey between the 4 and the 5 there. It starts to give. It starts to give way there up the top, in the middle column. Now, so at this stage we're going down to 3 bits per pixel. we've got 8 shades of grey. You could nearly count them at this stage. You know, whoops, that dark one there, 1, 2, 3, 4, 5. Yeah, and by the time you get over to the whites here, you could easily count up your 8. Still not bad, actually. So if this was a picture you were posting to Facebook on your house or something, the full quality 256 shades of grey, 8 bits per pixel, might have cost you 80 cents to send, and this one is only 30 cents to send in terms of size, the number of bits that are being sent. So that's an important distinction there. Save some money. At 2 bits per pixel, it's really posterized now. It's getting a bit chunky, getting a bit ropey. So there's 4 shades of grey here. Now we could easily count them. 1, 2, 3, and then the nearly white is 4. So of all the pixels in this, each one is only one of 4 possible shades of grey. There are 4 quantization levels used in the digitization here. And of course, if you go down to 1 bit per pixel, well, you know, you just get something like that. So there are 2 ways you can reduce the amount of data in an image. You can reduce the number of pixels, or you can reduce the number of colors. And those are 2 things we're going to look at over this class and the next class. But I want us to consider this again. When it comes to putting numbers on color, to put numbers on it, you need to put order on it, put structure on it. And it's very easy to organize different shades of grey. You know, if I lined up 10 different shirts here on a rack, and they were all shades of grey, I could say put them in order. Let's say I'm a freak and I like everything in my house organized. It'd be very easy to organize grey shirts in order. You could put the lightest ones at one end and the darkest ones at the other, and all the intermediate shades of grey in between. But color is a bit trickier. Color is not so simple. And what we're going to consider now is how you organize color, how you put numbers on color, because that's a different kettle of fish. So expressing levels of grey numerically is fairly easy. You put your white on one end, your black on the other end, you have different shades of grey, and there's just a question then of how many stops you have along the way. Do you have 256 shades, or do you go for 32 or whatever? So that's conceptually that's easy. But how do you put numbers on color? Green is different from blue. But is green more something than blue? It's more green, but what is it? How do you put order on color? If we were to line everyone up, if everyone was just wearing grey clothes, we could line them all up. But if we were putting everyone in order, if I said, right, everyone here now stand up on the wall and put yourselves in order of the colour of your clothes, the colour of your top. Okay, me in my white shirt, I might be at one end. Someone in a black top might be at the other. But does green come before blue? Actually, the Greeks used to think that the colours were something between black and white, because it was dark at night and it was light during the day, and when the sun was setting they saw these different colours. So it was reasonable to assume that colour was something that happened between black and white. But it's a bit more complex than that. So how do we put order on colour? How do we put numbers on colour? Like, are these colors in the right order? What does that even mean? We know what it means when the shades of grey. These are clearly in the right order. You know, they're in order there. But what about these? Well, there are a couple of different ways to put numbers on color. And we're going to look at, actually we're going to look at all four of them in varying degrees of detail. Okay? And the first thing we're going to look at is the hue, saturation, and brightness model, or the HSB model. So it turns out that the light that we can see is a small portion of the electromagnetic spectrum. I think it really freaks me out, actually. I still can't get my head around it, that the light we can see is the same kind of stuff as that's microwaving your dinner, or that's, you know, coming out of a radio station or TV station. It's actually the same thing. Like, radio and light are the same thing. We just experience them differently because we can see with our eyes. We can see a tiny portion of the electromagnetic spectrum. And we can't see, for example, infrared and ultraviolet. But some of the other species that evolved on the planet can see, you know, into this range. Or you can see it below. And of course, if you came from another planet, you might see something else altogether. Okay? So we can only see a portion of the electromagnetic spectrum. And this rainbow is important here because this features quite significantly. Now, so the portion we can see ranges from roughly 700 nanometers to 400 nanometers. So you can consider it in terms of wavelength or in frequency, and you might remember from your physics class there's a relationship between those. So we can order color by its frequency or its wavelength. So this is something that occurs naturally, you know, that range of values there. So we could say, well, look, the first thing we can use to classify color is we can look at its wavelength. So, you know, something that is, you know, has a wavelength of 500 might be here in the green, 700 there is at the red end, 400 there at the blue end. And that gets us so far. So we call that the hue. And so the hue of a color is somewhere where it kind of appears on the kind of rainbow scale, as I like to call it. So if someone has a red shirt, you know, the hue is somewhere there down the 700s. Someone has a yellow shirt, it's a bit lower, and so on. But there's more going on than just hue. I mean, there's no grey in here. There's no grey in a rainbow. There's no pink in the rainbow either, really. I mean, we know that the pink might be kind of come somewhere, certainly belongs somewhere in the reddish end. There's no actual pink in this rainbow. There's no black, there's no grey, there's no white. So there's more going on than just the hue. And look here, all of these colors actually have the same hue. So these are all somewhere in the blue range. All these yellows here, they all have the same hue. These all have the same hue, even though they're quite different. So it turns out that color can be diluted as well. So if you imagine a cup of coffee or a cup of hot chocolate, if you add some milk to that, it'll get lighter. If you add some more milk to it, it'll get lighter again. So you can actually wash out the color. You can dilute the color. Okay? And the strength of the color, or the purity of a color, is known as its saturation. So if the saturation is high, then the color is pure. and if the saturation is low, then it's grey. Which, if you think about it, is why the coffee and milk metaphor only goes so far, because if you keep adding milk to coffee, you'll get white, not grey. So all these colours have the same hue, but it tweaks the saturation. So this is a high saturation here on the left and low saturation on the right. So you have hue and we have saturation. Hue is the shade of the colour where it fits on sort of the rainbow scale, and the saturation then is how strong it is, how pure it is. So here I'm just tweaking the saturation. Saturation is different in these. But hue and saturation aren't enough to account for everything. All these here, these all have the same hue and the same saturation. Something else going on as well. And the third thing that you can change is the brightness. So brightness is a measure of how much light there is. So if you imagine you had a coloured light bulb and it had a very strong shade of red, so the hue would be red because it's a strong pure red as opposed to like a pink. The saturation is high, but if you had it on a dimmer switch, you could turn the dimmer switch up and down and you'd be altering the brightness. So if you turn the brightness down completely, it would just be black. Lights off. Now we're on familiar territory here because this is just like you would with a black and white image. It's just how bright it is. We can organize things by brightness fairly easily. So with hue, saturation, and brightness, those three values, you can get an accurate description of a color when you combine them. Now the black and white image, there was just one value. Just how bright is this? With color, you invariably need 3 or more values to get the job done. Hue is usually expressed as like a point on a wheel, the number of degrees, so 360 degrees. Saturation is usually expressed as a percentage. So you might have 100% or 50%. And brightness is usually expressed as a percentage as well. So it's a color wheel there where we have the hue around the edge, the brightness up and down here, and the saturation then is how far you are from the center. What I'm going to do is I'm going to just draw a shape on here. So you can do this with most software really. You can change the color here. No. So on a Mac, this is the typical color wheel. You get your different options. No. Can I make this bigger? Okay. So the best way to get to grips with any of the color systems actually is to crank up one of these. So it's not showing me the hue and saturation values, is it? No, domain opacity, no, that's different, okay? So hue is where you are on the wheel here. So as you go around it, the hue is changing. Please now it's not showing us the values. So as you go around the wheel, you're changing the hue. Okay. Here, the saturation is very high for this red. As I move towards the center, it becomes less saturated. See there, pink along the way, until you get to the middle, where it's so desaturated, you get white. And then brightness here then is just how bright and dark it is. So a dark green would need to be over there in the green somewhere. And then we could turn it up and down the brightness. But that's just too strong. Let's say we want a green that's more subtle. I'll be moving in here somewhere. Where's my yogi gone? Okay. So that's hue, saturation, and brightness. That's the most accessible color scheme that we have. It's the one that's most readily understood. We're familiar with the rainbow. Do you know what I mean? That's something that's natural to us. We're familiar with, purity and strength as a concept in the color, and brightness and darkness is something we're very familiar with as well. So that's the one that comes most naturally to humans. But most computer systems use other methods. Now, the Rgb system is by far the most widely used system in computers. So your TV would use something like RGB. Most images that you would store digitally would be stored using RGB. You may be familiar with this from secondary school, from your physics class. If you have a red light, a green light, and a blue light, and you shine them in the same place, all mixed together, you get white. You could even, I remember in physics class, we had like a wheel, and there was like the colors. It was like, kind of when you spin, like in the lottery. When you spin it really, really fast, they all blur together, and they do actually blur into white, which is hard to believe until you see it. So you have three values in the RGB system: red, green, and blue. The red represents how much redness is in the color. The green represents how much greenness is in the color, and the blue, go figure, tells you how much blueness is in the color. In the RGB system, we like to represent each of the variables as a value ranging from 0 to 255, which we can do then in 8 bits, which is where you sometimes hear the expression 24-bit color, because you've got 8 bits for the red, 8 bits for the green, and 8 bits for the blue. So if we look at this color here, this is pure red. Now, this color red here now is interacting with that projector, which is interacting with the light in this room and stuff. You can actually get devices, so like fashion designers now and stuff would carry these around with them when they're on their holidays. It's like, oh my god, that orange, I must find out exactly what that orange is. And you can actually put it up, to the device, and it'll say to you, that's whatever, whatever, whatever. I'm sure if I was to measure what this shade of red here coming off that screen is, it wouldn't be pure 255, It looks different on my screen. And that's an issue you always have with color technology. You must make sure that your displays are calibrated properly and things like that. But anyway, this color here, 25500, so this is pure red. The red is cranked up fully, and the green and the blue aren't at the races at all. Here we have red, green, and blue. No red, no green, and the blue is almost turned up fully. Well, 200 isn't all the way up here, but it's quite high. So it's quite a strong blue. Blue is the only thing featuring here, and because it's 200, it's quite high. When the red and the green are both cranked up fully, you get yellow, which isn't very intuitive. This is very different from mixing paints. When you're in primary school, you mix paints, and you got blue and yellow gave you green. But when you go to physics class, you're mixing light, which is a different scheme. We call them subtractive and additive. With paints, the more colors you add, the darker it gets. With light, the more light you add, the brighter it gets. So the higher the values in the RGB system, the brighter it is. Here we have no red. The green is at 178, which is about halfway, I think. And blue is 0. So just if you just had these numbers, you'd know that the only thing here at work is green. So you could easily speculate that it's some kind of green. The only question then would be, how bright or dark is it? Here, again, only green is in play. So there's no red, there's a bunch of green, and there's no blue. You notice that this time the green value is much lower than it was before. So the color is darker. So the higher the value, the brighter it is. The lower value, darker it is. If the red and the green and the blue are equal, then you're talking about a shade of grey. So here we have red 200, green 200, blue 200. That gives us a shade of grey, which is quite bright. Here, again, the red and the green and the blue values are equal. So we have a shade of grey, but the values aren't quite so high, so it's lower. It's darker. Oops. Here again, shade of grey, but 80, 80, 80 is darker. 255, 255, 255. The red is at maximum, green is at maximum, and the blue is at maximum. Here you get white. What do you think is coming next? When the red is 0, the green is 0, and the blue is 0, you get pure black. So as if you had 3 lights, a red light, a green light, and a blue light, and you turn them all off. Pitch black. If you only turned on the green light, you'd see green. In hexadecimal, in HTML, we express these values using hexadecimal. So you might remember seeing things like hash 8080FF when you're writing your HTML, on your style sheet. So here, for example, this color is red 128, green 128, and blue 255. That 128 is 80 in hexadecimal. The 128 is, for the green there, is 80 in hex, and then 255 is FF. So that's where you'd get hash 8080FF for that shade of blue there. Now, when we store an image then, for each pixel, we store a red value, a green value, and a blue value. And that tells us how, what color each pixel is. Sometimes it's instructive to view each of the colors separately. So inside in Photoshop, for example, you can look at just the red channel, just the green channel, and just the blue channel. And you might make adjustments to maybe just one of those channels. So in the pre-digital camera era, if you used a film that was designed for outside, indoors, with lighting like we have in here, everything would be a little bit green because those lights have a slightly green cast on them. If you had digitized that, you could alter the greenness by going into the green channel and tweaking it slightly. Things like that. So in the red channel, if you think about it, right, the color red has got high red values. And white also has high red values. So in the red channel, the difference between red and white is very hard to see. And you can see here that in this example, where there's red and where there's white, it's hard to see the difference. So here's the red channel, for example. You can see that the difference between the red parts and the white parts is hard to see. Whereas in the green channel, there's a big difference because red has a very low green value, but white has a very high green value. So there you see the difference between the red and the white parts very easily. And similarly, in the blue channel, the difference between the red and the white is easy to see. So you can do a lot of processing with images once you have them in digital form. So you can imagine if you have satellite photos, it may be hard to tell the difference between certain things, and if you tweak the colors and stuff like that, you can pick certain things out more easily, for example. You can imagine my delight when I saw 3 doors lined up in town in red and green and blue, all lined up there for me. So you can see that usually when we display the channels separately, they get displayed then as like black and white. So here, the door on the left is bright in the red channel because its red values are high. Whereas in the green channel, the first door, which is red, is quite dark, and you can see the lightest of the doors is the green one. And here in the blue channel, go figure, the blue door is the lightest of them, has the highest values. Okay, so let's get past that there. Now, there's another color system which is also used in computer systems. We don't see it as much. It mainly used to be used because it had a relationship, a fairly loose relationship now in fairness, with say the way analog television worked. And I'll explain to you what that is in a minute. But in the LAB system, again you have 3 values. But the LAB system has an interesting property in that the luminance part of the image and the chrominance information are separated out. I'll explain to you what that is. Okay, so in the RGB system, we break everything up into the red and the green and the blue. Okay? In the LAB system, we have lightness, which is the luminance. So the luminance is how bright or dark something is. And as humans, that's something we're very sensitive to. The lightness and darkness of something is something we respond to. I mean, if I was playing a game with you and I know we were all out there in the front and we had cones of different colors, right? And I said to you, right, everyone run to the one with the highest green value. You know, there'd be a bit of confusion. Whereas if I said run to the darkest one, you'd all very quickly, without even thinking, know which is lighter, which is dark. So lightness and darkness is something humans are very attuned to. And in the LAB system, we separate out the lightness into one channel, and then we use the other 2 for the color information. And looking at this here, you can see that in this image, I mean, most of the useful information is in this lightness part here. You can't even really make it out what it would be from just the color part. And that tells us something about the relative value of lightness versus color. The relative value of luminance information versus chrominance information to humans. So here we have the lightness channel. Then this part here represents half of the color information, and this here represents the other half of the color information. So the lightness, the L value, is the luminance, how bright and dark it is. And then the A value is somewhere here from, you know, green to red, and then B is somewhere from green to blue. So the color is somewhere in here. Would have an A value and a B value, and then you just got the lightness and darkness after that. So it's not a very intuitive system, apart from the fact that you can extract the lightness and darkness part very easily. So one useful property of this format is that if you had one byte representing the lightness, and then the next byte represented the A value, and the next byte represented the B value, and you had, for each pixel, you had those 3 values lined up, LAB, LAB, LAB. You could extract a very good black and white version of the image just by taking every 3rd byte. Get that L value, ignore the color. The next L value, ignore the color. The next L value, ignore the color. Whereas if you had an image in HSB or in RGB, well, you'd have to combine the 3 values and do some maths to extract the, black and white version well. Whereas you can extract a black and white version of an image in the LAB system trivially. You just ignore the color information as it comes in. And this is connected very, very loosely with the way analog television used to work, in that we had a black and white TV system, and then we were shifting to color. And okay, you could have redesigned the transmission scheme so that we had color TV, and then everybody would have to go away and buy color TVs to see that. But what actually we wanted was a system where if you had a black and white TV, you could still view the same signal as someone who had a color TV. And so what color TV did was it carried on transmitting the black and white image just as it always did, this image here. And then it also transmitted the extra information you needed to generate the color. So people with black and white TVs could still watch a color TV signal. More or less, I'm oversimplifying there now, hugely. So that's the main value of the LAB system, is that the luminance information is all lined up there for the plucking, just waiting to be extracted. And that's a useful property actually that we use, because if you take this image here, okay, of me, right? In this image, there's 24 bits per pixel. Now, what I've done is I separated out the luminance information and the chrominance information, and then threw away 15/16 of the color information. Threw away almost all of the color information. And you can hardly see the difference. The only place you see the difference actually is if you look really, really closely there at the red explosion. You can just make out, can't see the difference here, okay? Even though this would be 480,000 bytes, and this is 180,000 bytes. So this one has almost all of the color information removed, the one on the right. If you look closely here, you see it all right. The color there by the explosion is kind of screwed up. But that's just a good illustration of how much more important the luminance information is compared to the chrominance. So here I've kept the lightness and darkness information intact, and I've thrown away 15/16 of the color information. It's almost all gone. No, okay, I mean if this was the carnival in Rio or something, it would be a bit more colorful than me. You might notice it. If I was to do the same to the luminance information, you really notice it. So here, I have removed 15/16 of the luminance information, which was half the size actually of the chrominance anyway, but even then. And you can see it has a huge impact on the image. Whereas if you throw away a lot of the color information, it's not such a big deal. And that's because human vision sucks at color. We evolved color very, very late, and we're not as sensitive to that. We have much more sensitivity to lightness and darkness than we do to color. Which is why at night, for example, we can see things, but not in color. we think sometimes we can see the color of things at night in the dark because we know the color. But in fact, if you do experiments, when the light is very low, we can see at night, but we can't see color at night. And we can't even really make out color at our peripheral very well either. So humans are much more sensitive to luminance than they are to chrominance. And we can throw away a lot of the chrominance information and get away with it. And that's something we look at when it comes to how images are compressed, how we get them to take up less space. Okay? So we'll leave it there for today, and we'll continue the next day with a different color system again.